Okay, so if you're there, hi. We will be able to watch this on the replay, totally fine. But we're going to go through tonight a lot of stuff about the second derivative because this tends to be an area where people struggle just because there are so many different things going on. There's so many different things you should be thinking about. And so I want to talk about this because it's been a problem area for us. So again, last reminder, that remind code down below me. Feel free to send me reminds at any time or chat in the box on YouTube. I have that open too. So you can send me a chat or you can send me a remind. Either way, this is for you. So send me as many questions as you guys have. All right. So two things that the second derivative should make you think about. Whenever you see a second derivative, you should first of all be thinking about concavity. So if the second derivative of a function is positive, that means that function is concave up. If the second derivative is negative, that means that function is concave down on that particular interval. The second thing you should be thinking about is the tangent line. So if something is concave up, the tangent line has to lie below it. And so that's going to have implications, especially when I talk about approximating, because if my tangent line is down here and my value of my function is up there, I'm going to see that that's an under approximate for the actual value of the function. Same thing for when something is concave downward, right? If something's concave down, my tangent line is going to be above it, and so that means that that is going to be an overestimate. If I pick a particular point there, it would be over the curve. So really when I talk about a second derivative, pretty much everything we do tonight is going to come back down to this. So either we're talking about being concave up, concave down, or we're talking about approximations. And there's three big ideas I want to go through tonight. Number one is calculating second derivatives in some tricky scenarios. Number two is analyzing with second derivatives. And number three is approximating with them. So we're going to start with calculating. Just like last night, we're not going to do every question, but I'm going to kind of go through and pick some ones that we've been struggling with. And if you have particular questions, send them to me because that's what we're here for. So this first one, they've given me this function. There, you guys can see it now. X plus 2y times dy dx equals 2y minus x. Evaluate d squared y over dx squared at the point 3, 0. So immediately I see that I have a dy dx in here. This is a differential equation because it has a dy dx in it. So what I need to do to calculate my second derivative is I need to isolate dy dx, and then I'm going to take a derivative from there. So if I do that, I'm going to divide both sides by x plus 2y. So dy dx is 2x minus y over x plus 2y. And then from there, I want to find my second derivative. So d squared y over dx squared equals, anytime I take a derivative of a fraction, I'm doing quotient rule. So low x plus 2y, d high 2 minus y prime. Low d high minus high, which is 2x minus y. D low, which is 1 plus 2y prime. All over low squared, so x plus 2y squared. And then we want to plug in from there. And the key thing here is anytime you see y prime, that is the same as dy dx. So when I plug in 3, 0 for dy dx or y prime, right, plug in 3, 0. So this is going to give me 6 minus 0 over 3 plus 0. So this equals 2. So that's y prime. And I know x is 3 and y is 0. So this is going to equal 3 times 2 minus, and dy dx was 2, minus 2x minus y is 6 times 1 plus 2y prime is 1 plus 4, all over low squared, so that's 3 plus 0 squared. So that's going to give me 0 here. This is going to give me negative 30 over 9. Simplify that down, and that gives me negative 10 over 3, which is A. So implicit differentiation, finding a second derivative, not too crazy. All right, let's look at the next one, just calculating again. And this is our last calculating one, and then we're going to go into some analysis. So f and g are twice differentiable. All that means is you can take a derivative twice. And h is f of g of x, so I want to find h double prime. So I'm going to start by finding h prime, right? You need a first derivative to get a second. So h prime is going to be this is chain rule, derivative of the outside, leave the inside alone, times derivative of the inside. And now I need h double prime. And so I need to really analyze what's going on here. So on this part, we have some chain rule. And on this part, we have some product rule, right? Those are being multiplied. So I'm going to do derivative of the first times the second plus derivative of the second times the first. So derivative of the first is going to be f, let's do this in pen, f double prime of g times g prime. That's derivative of the first, times the second, which is g prime, plus derivative of the second, which is g double prime, times the first, which is f prime of g. And then we just need to simplify this. And so this is where this gets a little bit tricky, is what can you simplify here? So, do I see anything in common? Well, I see two g primes there. So this is f double prime of g times g prime squared plus g double prime of x times f prime g. So let's see what that looks like on our answers. So I see f double prime of g, g prime squared, f prime of g times g double prime. That would be it. So that's kind of where I'm going to leave it for calculating. We will do some more calculating in these next problems, but that's where I'm going to leave it for right now with calculating, and we are going to move on to some analysis, and that is where we start to run into problems normally. So a couple things we can do with a second derivative. Number one, we can find points of inflection. Number two, we can find concavity and where it changes. Number three, we can look at particle motion, especially acceleration. And we can always find maxima, minima, all of those things. So that's what we're going to be looking at here. So on this first one, it says this is my second derivative. So notice they've already given it to you. You don't need to do the work for it. Find where f has a point of inflection. The key here is that points of inflection don't just happen when f double prime equals 0. They happen when f double prime changes signs. So you need to have a stronger argument than just that's where it equals 0. You need to actually show that it changes signs. So let's start with that. Where would this equal 0? So your critical values of this would be at -1, at 0, and at 2. And I'm going to think about the behavior here. So I know at 2 it's going to be tangent, right? You've got a multiplicity of 2. So it definitely isn't going to change signs there. But it should change signs at 0 and at -1. Now, if you want to check yourself here, you can. So checking myself here, I could plug in any value less than -1. So let's say I plug in -2 for down here. That would give me a negative, and then a positive. So that would be positive. And then I'd have to plug in a value between -1 and 0. So let's say -0.5. That would give me a negative, a positive, and a positive. So that's negative. Then when I would have to plug in a value between 0 and 2, so let's say I plug in 1, positive, 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 and same thing for bigger than 2, it's still going to be positive. So notice this was tangent here, it didn't actually change signs, so your points of inflection are just at -1 and at 0 only. Okay, please send questions if you have them. Find the x-coordinate of the point of inflection. This would be the exact same thing, except you are not given the second derivative. So I'm going to find my second derivative, y double prime equals, or y prime, let's start with that, is x squared plus 10x, right? Derivative of 24 is 0. And so y double prime would be 2x plus 10. So my only critical value here of the second derivative is at x equals -5. So I need to check and see if it actually changes values there, which I'm going to guess it is because none of the answers are no points of inflection. But let's double check. Second derivative, if I plug in a number less than -5, this is negative. Greater than -5, this is positive. So my critical value, or my, point of inflection is at -5. Okay, next one. So this is a graph of the second derivative. Find all intervals on which the function is concave downward. So concave downward to me implies that f double prime is negative. Negative is anywhere that we are, let me make this a little bigger, below the x-axis, right? That's where f double prime is negative. So this would be going from, notice my interval, starting at -2, -2 to -1, union 1 to 3. And so I'm looking for that in my answer choices, which would be E. Again, if you understand these, they're normally pretty quick. All right, next one. This would be the same thing on the calculator. So this is f prime. Which of the following are intervals where f is concave downward? So you need to look at the second derivative and look at the graph of it and go from there. Now the problem is they gave you the first derivative. So to find the second derivative, you are going to need to do some chain rule. Your calculator can find the derivative at a point, but it cannot find a formula for the derivative, not the TI-84s. So what I'm going to have to do is take the derivative of this by hand, and then I can look at the graph. So derivative of this, okay, derivative of e to a power is e to that power times the derivative of the inside, the power, which would be 4x cubed minus 4 x. It should be 2x squared. And derivative of -2 is 0. So this I would plug into my calculator, look for where it's negative, below the x-axis, and that would give you your values there. Okay, let's keep going. Position of a particle moving along the x-axis is given by x of t equals sine minus cos. What is the acceleration when the velocity first equals 0? So I'm going to be very careful with notation here. We're going to talk about this more in our live stream tomorrow night, which is going to be all particle motion. And you need to be a little careful with your notation. Now, I know this is multiple choice, so it doesn't really matter, but we're still going to practice carefully because what you play how you practice, right? So if this is x of t, that's position. So x of t is sine t minus cos t. I know that the derivative of position is velocity, but I can't just say, oh, this is v of t, because that's not a defined function here. So I'm going to say that this is x prime of t. If you would like to define that as v of t, you may, but you have to at some point say that equals x prime of t. So derivative of sine is cos, derivative of cos is negative sine, so that would be the first derivative. And the second derivative, which you could define as a of t, again, you're making that up, you need to define it, would be derivative of cos is negative sine, derivative of sine is cosine. So it says, what is the acceleration? So I'm going to plug into acceleration when the velocity is first equal to 0. So I'm going to take my velocity function and set it equal to 0. So it's going to be cosine of t plus sine of t equals 0. So cosine of t has to be the opposite of sine of t. Okay? So think about where that happens. They have the same value, absolute value, at reference angles of pi over 4. So think about your unit circle, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And I want to know when this first happens. And they tell me t is greater than 0. So that gives me the interval, sorry. So in this quadrant, sine and cos are both positive. So it's not that. In this quadrant, sine and cos are opposite signs. One is positive, one is negative. So the first time this happens is at t equals 3 pi over 4. So now I need to plug that in to my acceleration function. So now I can say x double prime of 3 pi over 4, or you could say a of 3 pi over 4 if you've defined it, would be negative sine of 3 pi over 4 plus cos of 3 pi over 4, and sine of 3 pi over 4 is positive radical 2 over 2. Cos of 3 pi over 4 is negative radical 2 over 2. So that is just negative radical 2. That should be A. Okay. Again, keep sending questions. This next one's kind of weird, and it's because it's talking about the maximum acceleration. So you are given here velocity. So I know my acceleration function, and if I want to call it A of t, I need to define that as v prime of t, is 3t squared minus 6t plus 12. So that is the acceleration function. It does not say what is the acceleration, right, at 4. It says what is the maximum acceleration. So we want to maximize this. And anytime we maximize something, we're taking the derivative of it, we're finding the absolute max or absolute min. So that's what I'm going to do. So I'm going to find a prime of t, which is v double prime of t, and I want to find the actual maximum. So this is going to be 6t minus 6. So my critical value here is at t equals 1. So what I need to do here is test my critical value and test my endpoints. So critical value here is at 1. That's on the interval, which is good. Endpoints are 0 and 3. So I have t, and I want a of t, or v prime of t. So if I plug in 0, I just get 4. If I plug in, nope, I need to plug that into my derivative. So if I plug in 0, I get 12, right, plugging it into the acceleration function. If I plug in 1, I get 3 minus 6 plus 12, which is going to be 9. And if I plug in 3, I get 27 minus 18 plus 12. So that's 27 minus 18 is 9, plus 12 is 21. So my maximum there is 21. Okay, we've got a couple more of these, and then we're going to talk about approximating. So the next one says f is closed on the closed interval 2, 5. F has a positive first derivative, so that means that f is increasing, and a negative second derivative, so that means it's concave down. F is concave down, that is. Don't say it. Which of the following could be the graph of the table? So first of all, I'm going to get rid of anything that's not increasing. So this is increasing, that's decreasing, that's decreasing, that's decreasing. So I've already gotten it to either A or B. Now I need to figure out the one that's concave down. So the way to look at that is to look at the way that it's changing. So here, this goes up by 2, this goes up by 3, this goes up by 4. And if you look at the rate that that's increasing, it's increasing at an increasing rate, which tells me that my second derivative, the rate is changing, is positive. This one goes up by 4, then goes up by 3, then goes up by 2. This one is increasing at a decreasing rate, which tells me my second derivative is negative. Now, if you're in doubt, graph it. If you're in doubt, graph it. So, okay, 2, 7, 3, 9, 4, 12, 5, 16. That's going to start making that kind of curve up, right? Versus 2, 7, 11, 14, 16. That's going to start making that kind of curve. So graph them if you're not sure. Okay, you guys are so quiet. All right, next one. This is my graph. My chart. A polynomial function has selected values of its second derivative. So this is f double prime given in the table. Which of the following statements must be true? So I know that it's concave up right here. I know that I can't really tell right there. I know that it's concave down here. I know that it's concave up here. So let's think about what we know. Do we know that it's increasing on 0 to 2? I have no idea. No clue what the first derivative is doing. so I can't tell this. Likewise, for the second derivative, I have no idea. There's not enough information given. Or for B. For C, it has a local max at 1. I really don't know. I know that this happens to be concave up, and that happens to be concave down. I know that the second derivative is 0, which means I can't tell whether it's a max or a min. I don't even know if it's a critical value. So again, not enough information there. There's a point of inflection at 1. Do I actually know that? Well, it does look like it goes from positive to negative. But I have no clue what this does between 0 and 1, and I have no clue what it does between 1 and 2. So even D is too specific. I really don't know. So let's look at E, which is really the most broad. It changes concavity somewhere in the interval from 0 to 2. If I know it's a polynomial, I know it's continuous, I know it's differentiable. So if I see that this goes from a positive second derivative to a negative second derivative, it has to change signs at some point, which means the second derivative does, which means the function has to change concavity. So I don't know that it happens at 1. It could just be tangent there, but it has to happen at some point. So it has to be E. Okay, keep sending questions. All right, so we've got 2 free responses here, 3 free responses here. We are not going to do all of them, but we're going to do kind of bits and pieces from it. And some of them lead into each other. These are all released AB questions, so they are all free responses that you would possibly have seen or could see. So on this first one, it says f is a function defined by this, k is a positive constant. So first thing we want for part A is f prime and f double prime. And that's going to play a part in what we do after, so I'm going to do A and B. So for A, f prime of x would be, k is just a constant, so I'm just going to leave it out front, times, let me go down a little bit, 1 over 2 radical x, and then derivative of ln x is 1 over x. And my second derivative, so take the derivative of that, k, again, is just a constant. I'm going to put the 1/2 right here, and think about this as k times 1/2 times x to the negative 1/2 minus x to the negative first, right? So on this first part, you can bring your negative 1/2 down. That would be x to the negative 3/2 minus, bring your negative 1 down, x to the negative second. So there's my first derivative, there's my second derivative. It does not ask me to simplify, so leave it. So then it says, for what value of k does f have a critical point at 1? So think about this. A critical point means that either your first derivative equals 0 or your first derivative is undefined. So I'm going to look at my first derivative, and I'm going to say, okay, either this equals 0 or it's undefined. At 1, this can't be undefined because you would have 1 as your x and your y. So I'm going to say, okay, then that means that this equals 0. So 0 should equal k times 1 over 2, because we're plugging in at x equals 1, minus 1 over 1, which is 1. So add 1 to the other side, 1 equals k over 2, so k equals 2. So that's my value of k. And then it says, for this value of k, determine whether f has a relative min, relative max, or neither. Now, could you do a sign chart, test both sides? Sure, you can. But if you know it's a critical value, you could also just plug into the second derivative, because that's going to tell me whether this has an absolute max or an absolute min. So if I plug into the second derivative, f prime double prime of 1, when k equals 2. So that's going to give me 2 times 1/2 times negative 1/2, and then 1 to any power is 1. Plus 1, right? X to the negative second is just 1. So this gives me negative 1/2 plus 1, so this gives me 1/2. Now think about this. I know that this is a critical value, and I know my second derivative is positive. So that means that f is concave up there, right? So because f prime of 1 equals 0 and f double prime of 1 is greater than 0, f must have a relative min at x equals 1. Again, you could do a sign chart and test it, but it's much faster to just go straight to the second derivative. Okay, send questions if you have them. Let's look at part C. This says for a certain value of k, the graph of f has a point of inflection on the x-axis. Okay, look at this one. So, consider the curve given by x squared plus 4y squared equals 7 plus 3xy. So, first thing says show that dy dx equals 3y minus 2x over 8y minus 3x. That is a implicit differentiation problem. So, go ahead and do that. I'm going to leave that to you guys, but we're going to go on to the next two parts. Part B, show that there is a point with x coordinate 3 at which the tangent line is horizontal. A horizontal tangent line means that your first derivative equals 0. So what you would be looking at is setting your derivative equal to 0, plugging in 3 for your x value, and then going there. I want to look at part C. It says find the second derivative. Does this curve have a max, min, or neither at point P? Justify your answer. So we need point P from part B to do this one. So part B, show that there is a point P with x coordinate 3 on which the line tangent to the curve is horizontal. So part B, so if it's horizontal, dy dx is going to equal 0. So I'm going to take that and set it equal to 0. So 3y minus 2x over 8y minus 3x equals 0. And they tell me with x coordinate of 3. So, x coordinate of 3, right? That's what I get there. And so I want to see what y comes out to be here. So this is 3y minus 6. This is 8y minus 9 equals 0. I only care about where the numerator equals 0 if my fraction comes out to be 0. So that's 3y equals 6, so y equals 2. Now, I don't know if that's actually on the curve. So the point that I'm looking at here is 3, 2. I need to verify that's actually on the curve. So I'm going to plug it into this and hope that it comes out correctly. So this is going to be 3 squared plus 4 times 2 squared. And I want to show that that equals 7 plus 3 times 3 times 2. So this is 9 plus 16. This is 7 plus 18. Either way, I get 25 equal to 25. So that's how I know that the point is actually on the curve. So this is my point. Now I want to see, is there a min, max, or neither? And I want to justify. So I already know that my first derivative equals 0 there. So I already know that this is a critical value. So now what I need to do is look at my second derivative. And so second derivative, let's find that. So d squared y over dx squared equals quotient rule. So I'm going to do low d high, which is 3y prime minus 2, low d high minus high d low. Let me shrink this a little bit. Minus high d low, which is 8y prime minus 3, all over low squared, which is 8y minus 3x squared. I know that y prime at that point is 0. I showed that in part B. And I know my point is 3, 2. So let's plug this in. So this is going to be 8y. So 8y is going to be 16 minus 9, right? 3, 2. And then this is going to be 0 minus 2 minus 3y is going to be, what was y again? 2. So 6 minus 9 and then 0 minus 3 over 8y, which is 16 minus 9 squared. So this gives me 7 times negative 2 minus negative 3 times negative 3 all over 16 minus 9 is 7 squared. I really just care about the sign of this. I care about whether it's positive or negative. You could leave it there on the free response, right? So this is negative 14 minus positive 9 over 49. And all I know is that that's less than 0. So knowing that my second derivative is less than 0, I could say here that there is a relative, think about it, less than 0 means concave down, relative maximum. There exists a relative max on f of 2 at x equals 3 because it was f, right? Oh no, it was y. Sorry, on y. Because dy dx equals 0 and d squared y dx squared is greater than 0 at 3, 2. So again, second derivative, think concavity. If it's negative, it's concave down, which means it's a maximum. All right. This one we're going to skip over because we already did this one in class, actually. Okay, last thing we're going to do is we're going to approximate with this, and then I will answer any questions, and then we're out for tonight. Tonight's a little bit shorter. So, approximating with a second derivative. Again, think concavity, think tangent line. So, f is twice differentiable, just means we can take a second derivative. F of 2 is 1, f prime of 2 is 4, and f double prime of 2 is 3. So, here's what I know. I know that that's the actual value of the function. I know that that tells me that the function is increasing. I also know it's not a max or min. And I know this tells me that it's concave up. So what is the value of the approximation of f of 1.9 using the tangent line to the graph at x equals 2? So let's take a look at this. I know that y minus 1 should equal 4 times x minus 2. So that's my tangent line. I want the approximate at 1.9. So it's going to be y minus 1 equals 4 times 1.9 minus 2, which is y minus 1, is 4 times negative 0.1, negative 1/10. And so y equals 1 minus 0.4. So this is 0.6. So I'm getting this here. This is extra information, but what I should be able to do with this is say, okay, this is concave up. This is below the curve. So that should be an underestimate. It's definitely below what we think it should probably be. And so I could tell you whether it's an under or an over approximate there. Okay, last question. We're going to go potato on this one because this was one we struggled on continually. So it asked me in part A for a tangent line to the graph, and then it asked me to analyze from there. So let's look at this. A potato is being taken from a pot. The internal temperature of the potato is 91 at t equals 0. That is your initial condition, right? And it's greater than 27 for all times t greater than 0. So we know that this is the differential equation it satisfies. And like I talked about in the live stream last night, if this confuses you, then make this dy dx. And so this would be negative 1/4. Think about h as y minus 27. And so that can sometimes help, just thinking about it in terms of variables you're more used to. So the tangent line here, I'm going to plug in. So y minus 91 equals, I know, actually this should be, yeah, this is okay, x minus 0. And my slope there, you're going to plug into that equation. So it wants me to plug in h. So I'm going to find dh dt at when h is 91. So it's negative 1/4, 91 minus 27. And so that gives me negative 1/4, 91 minus 27. I don't know why this is hard for me right now. Is not that. 64. And so that is negative 16. So this is going to be negative 16. So that is my tangent line. And I want to approximate the internal temperature at when x is 3 or when t is 3. So I'm going to plug in 3 there. And so this is going to be y minus 91 equals negative 16 times 3. Add 91 over. So y equals negative 16 times 3 plus 91. You do not need to simplify that. Okay, that's my approximate degrees Fahrenheit. And then it asks me to find the second derivative and determine whether it's an over or an underestimate. So the second derivative of this, think about dh dt, again, think almost like a dy dx. So d squared h over dt squared is going to be negative 1/4 dh dt, because it's like a y, right? And then the derivative of 27 is 0. So this, it says in terms, well, I want to figure out what this is. It doesn't say in terms of anything. So this would be negative 1/4. dh dt is negative 1/4 h minus 27. And so think about it. These two together would wind up being positive, right? And it tells me that it's greater than 27 for all times. So this is always going to be greater than 0. If it's greater than 0, therefore h is concave up. So the tangent line's below it, right? So the tangent approximation is an under approximation. Okay. So, second derivative, you're always thinking about concavity. You're always thinking about tangent lines above or below. I'm going to hang out here for a couple minutes. Thank you to those guys that tuned in live. For anybody who is watching on the replay, thank you for watching on the replay. You're awesome. And I will see you guys later. Send me any questions. I'll be here for a minute.